Hi everyone, my name is Alexis Geislink, and the paper I'll be presenting is called An Integrated Hardware-Software Verification and Validation Methodology for Signal Processing Systems. So, as we all know, any engineering organization that is designing a product will have design teams that create specifications for the product and the design that relate to the functionality, what it actually needs to do, and the objective, the size, the cost, efficiency, and standards and laws and certifications that they're trying to get and trying to abide by. So the verification and validation processes are enacted to ensure that the final product and the final design is complying with all of these various specifications, and they do that through different testing and modeling methods. Here you can see a generic diagram for a design process. So the author of this paper conducted interviews with clients and was able to break down electronic systems development process into three main phases, which are the system design phase, where the end goal, the final design, is conceptualized as just one unified system, considers all these different specifications, and then in the hardware software design phase, they will separate the design into the hardware and the software components, and typically separate organizations implement those different components independently. And then finally, the integration and testing phase are when the hardware and software components are joined and it becomes a complete system. And that is typically when final systems testing and validation occurs. So you can see on the right that typically there is a separation of the software and the hardware design and the software and the hardware validation before the final systems integration at the bottom. So as we just said, the V&V processes for the software and the hardware components are typically carried out in parallel, separated from each other before the system is brought together, before the system integration and validation phase. So during that phase, problems are very common there because of a variety of things, such as misinterpretations between the two groups that are designing the software and the hardware, poorly communicated design changes if something changes and the two groups don't correctly communicate how to adapt to that with regard to each other, and a lack of performance modeling, etc. So due to the time and the cost of redeveloping the hardware, typically they will try to mitigate any issues with software, which still results in, reworking of the software, loss of time, budgetary losses, and potentially a loss of features if the hardware is so non-compliant that the software cannot be carried out correctly no matter how it's adapted. There are various methods of verification and validation depending on the specific specification that you're trying to verify. Specifically, hardware and software co-verification is necessary to ensure that the embedded system software correctly operates on the final hardware design, so to ensure that the two are working properly together, and that's going to happen at that integration phase. Model-based design and development tools are typically standard in the engineering industry for validation processes. We have graphical modeling, which will represent the system as a black box, or more commonly for more complex systems, multiple connected black boxes corresponding to the various subsystems, and they'll have inputs and their logical outputs depending on what that subsystem is supposed to be doing. And then you have code that will evaluate the system performance, and you can apply that at different levels and different interfaces of the system, ideally moving closer to the total system integration and measuring against all the known specifications for the different subsystems. So one of the big ideas that they're proposing with this paper is to integrate the design process with the V&V processes throughout instead of focusing them at the end in that integration phase. So applying V&V procedures to earlier stages of the design and development would likely result in significant cost and time savings and reduce design rework. So instead of finding out that you have a problem at the very end, you can kind of catch it and correct it along the way. An integrated approach could simplify the overall process, which typically involves using many different tools and databases to satisfy the project requirements and keep track of all the different subsystems and all that. A V-gap bridge process would integrate model-driven design to increase concurrent innovation, improve traceability and navigation through the various design stages, and apply early and/or all-stage testing for a more streamlined design process. Generally, the platforms that we use for verification and validation are hardware emulators and FPGA prototypes. So high-level hardware emulators have capacities of several billions of ASIC equivalent gates. They compile testing designs with great speeds and throughput levels, and hardware debugging is facilitated by their design visibility and their bus tracing abilities. And then FPGA prototypes offer less flexibility and hardware debugging features, but they have much faster execution speeds, making them ideal for processing large software throughputs. According to the paper, the 5 main differences between hardware emulators and FPGA prototypes can be summarized as design capacity and scalability, compilation speeds, execution speeds, design debug capabilities, and use models. Recently, enterprise FPGA prototypes have emerged as a desirable compromise between these two methods. They offer similar capacities and scalabilities as the hardware emulators, while maintaining execution speeds, making them a good option for V&V application at various stages of the design process, as they can apply to both the hardware and the software side of things. So there's also a need for hardware-software hybrid verification environment, as traditional designs involve hardware development using Verilog or VHDL, and software development is usually done using assembly language, C or C++. So a hybrid environment would facilitate systems integration early in the design process, and it would help catch integration issues early on while they're less costly to fix. As a summary of the paper, V&V verification and validation is the process of confirming that a design in a product meets various specifications set forth in the early stages of the design. Hardware and software co-verification is typically done toward the end of the process, but it can be done with early integration of the software on the hardware using SoC verification techniques to verify that the embedded system software runs as desired on the hardware representation. This has high potential for time and cost savings, as integration issues will be caught earlier on in the process when they're easier and less costly to fix. And then here we have the citation for the paper. The link to the paper will also be posted in my comment above, so I'm looking forward to speaking with everybody about this. Thanks.